Duality theory. I have divided this lecture into 4 parts. Part 1 has to do with the primal. Later on, parts 2 and 3 have to do with the dual, and part 4 has to do with a graphical illustration of duality theory. Constraint optimization problem. So we minimize with respect to x, which is in n dimensions, the function f of x subject to the inequality constraints gix is less than equal to 0. I belongs to script I. This is the set of equality constraints. And hjx is equal to 0, where j belongs to E, script E, that's the set of equality constraints. The Lagrangian for this constraint optimization problem is f of x plus summation lambda I gi of x. This term corresponds to the inequality constraints, and lambda i's are the Lagrange multipliers or dual variables for the inequality constraints. And the third term is summation j mu j hj of x. Mu j's are again Lagrange multipliers, but they correspond to the equality constraints. The Lagrange multipliers lambda i's that are for the inequality constraints must be greater than or equal to 0. There is no such constraint for the mu j's. The constraint optimization problem can be expressed more concisely using vector functions. So gx is less than or equal to 0, where this g is a vector function, Boji, of inequality constraints, which is a mapping from n dimensions to L dimensions, where L is the cardinality of the set of inequality constraints. Likewise, hx is equal to 0, where h contains all the equality constraints. It's a vector function that maps the n dimensions to m dimensions, where m is the cardinality of the set of equality constraints. The Lagrangian for this COP can now be expressed more succinctly too as f of x plus lambda transpose g of x plus mu transpose h of x, where lambda and mu are vectors. The feasible set F is the set of all points x that are feasible, that is, for all I in the set of inequality constraints, gi of x is less than or equal to 0, and for all j belongs to the set of equality constraints, hj of x is equal to 0. The primal function is theta p of x, which is supremum with respect to the dual variables lambda greater than or equal to 0 and mu of the Lagrangian, which is supremum of f of x plus lambda transpose g of x plus mu transpose h of x. And expressing the Lagrangian as scalars, this is supremum with respect to lambda I greater than or equal to 0 and mu j of f of x plus summation lambda I gi of x plus summation mu j hj of x. There's a slight misuse of notation here. This lambda I greater than or equal to 0 means that we're carrying out the supremum over all possible lambda i's greater than or equal to 0 and over all possible mu j's. In fact, all possible dual variables. Therefore, we are eliminating lambdas and mu's. By doing the supremum over them, we are eliminating lambdas and mu's from the Lagrangian, and that gives us a function of only x. So theta p of x is a function of x. It's not a function of the lambdas and mu's. Therefore, theta p is a mapping from n dimensions to the real line, which is the same as the objective function. A mapping from n dimensions to the real line because the only argument to theta p of x is x, since lambdas and mu's have been eliminated. Now, since this is an important expression, let's highlight it. Theorem 1, in the feasible region, the primal function is equal to the objective function, and in the infeasible region, the primal function is infinite. In other words, theta p of x, which is the primal function, is equal to f of x when x is feasible. And it's equal to infinite when x is not feasible. Let's highlight this theorem and proceed with the proof. Proof. By definition, theta p of x is the supremum with respect to the lambda i's greater than or equal to 0 and the mu j's of f of x plus summation lambda I gi of x plus summation mu j hj of x, which is equal to f of x. I bring f of x outside the supremum because it doesn't contain the lambdas and the mu's, so it's independent of the lambdas and mu's. I bring it outside. So supremum of, f of x plus supremum over the lambdas and mu's of summation lambda I gi of x plus summation mu j hj of x. Now we will examine two cases separately. X belongs to f, this case, and we shall show that theta p of x, the primal function, is equal to f of x in this case. And then we'll examine the other case, case 2, where x is infeasible, x does not belong to f, in which case we shall show that theta p of x is infinite. Now let's look at the primal function theta p of x when x is in the feasible region. That's case 1. X is feasible when all the inequality constraint gi of x must be less than or equal to 0, and likewise all the hj's of x must be equal to 0, the equality constraints. Let's look at the inequality constraints first. Gi of x is less than or equal to 0 in the feasible region, and lambda I must be greater than or equal to 0. So gi and lambda I are of opposite signs. Their product, lambda I gi of x, must be less than or equal to 0. Now let's look at an equality constraint. Hj of x is equal to 0, whence, as long as mu is finite, mu j hj of x is also equal to 0. Therefore, let's look at the supremum of summation lambda I gi of x plus summation mu j hj of x. Each term in the first summation must be less than or equal to 0. And each term in the second summation is equal to 0. So the first summation can only have a negative or 0 value, and the second summation here can only be 0, whence the supremum of them is equal to 0. Therefore, theta p of x is f of x plus supremum over lambda i's and mu j's of summation lambda I gi plus mu j hj must be equal to f of x, because this supremum equals 0. Therefore, when x is feasible, theta p of x is equal to f of x. This is the first part of our theorem, which we just proved. Now let's move on to the next part, when x is infeasible. When x is infeasible, infeasibility could arise due to two cases. One is when an inequality constraint gi is greater than 0, or when hj is not equal to 0. Let's look at the first situation where the infeasibility arises because there is at least one constraint which is violated, and that constraint is a GI, an inequality constraint is violated. Therefore, for some I, we must have GI of x is strictly greater than 0. Furthermore, lambda I has to be greater than or equal to 0. Therefore, their product lambda I GI of x is always greater than or equal to 0. Theta P of x is f of x plus supremum of over all the lambda I GI of x's, and when we let lambda I equals infinity, then lambda I GI of x becomes equal to infinity. So regardless of the other terms and f of x, this term here becomes infinite when we do the supremum over the lambda i's when GI of x is greater than 0. Therefore, theta P of x is equal to infinite. Therefore, when GI of x is violated, theta P of x is equal to infinite. So we looked at when x is infinite and when x is, infeasible and a GI of x is violated, then theta P of x is equal to infinite. And that's part of case 2 of our proof. Now we will look at the other situation where an equality constraint is violated. Now let's look at the primal function when x is infeasible, but this time the infeasibility arises because of a constraint violation. Hj is not equal to 0. All the equality constraints are of the form hj of x equals 0. Now suppose this hj of x is violated so that it's not equal to 0. Note that the corresponding Lagrange multiplier mu j can be of any sign because h is an equality constraint. Now we let the sign of mu j be equal to the sign of hj. Hj obviously has a sign which is either positive or negative because it's not equal to 0. Hence, mu j hj, their product, has to be strictly greater than 0. Now, theta p of x is equal to fx plus the supremum of mu j hj of x plus other terms. So what's the highest value of mu j hj of x when we adjust mu j? And we let mu j equal infinite, but with the same sign as hj, so that mu j hj becomes equal to infinite. So the maximum value of mu j hj, supremum, is infinite. Hence, theta p of x is also equal to infinite. Thus, we saw that when an equality constraint hj of x is violated, then the primal function theta p of x becomes equal to infinite. And this illustrates the second situation of our case 2 when x is infeasible. So theta p of x is infinite in this situation corresponding to case 2 as well. Graphical illustration of theorem 1. In this illustration, we shall focus on only a single dimensional x. So that's along the horizontal axis. And the green region here is the feasible region, and the regions shaded gray are infeasible. F bar. This is the function f of x. And this is theta p of x, the primal function. In the feasible region, theta p of x is equal to f of x. And in the infeasible region, theta p of x becomes infinite. We can remove f of x and look at. So this is theta p of x. In the feasible region, theta p of x is equal to f of x. Why is that? Because the constraint terms of the Lagrangian can never exceed 0 when we are in the feasible region. But in the infeasible region, the constraint terms become infinite. We can adjust the Lagrange multipliers, lambdas, or the mu's and set them to infinite so that the theta p of x becomes equal to infinite. So this is the primal problem, theta p of x, which is by definition the supremum over lambdas greater than or equal to zeros and mu's of the Lagrange function Lx lambda mu. And we just saw from theorem 1 that theta p of x is equal to f of x when x is feasible, and theta p of x is equal to infinite when x is infeasible. Primal problem. The primal problem is to minimize theta p of x, the primal function. The primal problem removes constraints. We don't have any constraints when we do the minimization of the primal function theta p of x. This is unlike the original optimization problem, which had inequality and equality constraints. Corollary. The solution of the primal problem is the constrained optimum. In other words, x star, if this is the solution to the original COP, then x star is equal to arg infimum with respect to x of the primal function theta p of x, which is equal to arg inf of with respect to x supremum with respect to lambdas and mu's of Lx lambda mu. In other words, theta p star, let this be the minimum of the primal function, then theta p star is equal to theta p of x star. Let's highlight this corollary. This is the graphical illustration of the previous corollary. So instead of minimizing under the constraints the original function f of x, if we simply minimize the primal function theta p of x, then the minimum will be equal to the minimum of the constraint optimization problem, x star. And that's because in the infeasible region, theta p of x becomes equal to infinite. And it only stays finite unless f of x is infinite. So it stays finite only in the feasible region. So when we are minimizing theta p of x, we get a minimum which is always in the feasible region, and that coincides with the solution of the original constraint optimization problem.